Yeah, thank you, Vedika. And I want to thank the organizers for this opportunity to talk about our recent work. So this is based on a paper we recently posted on arXiv with the same title. And I want to thank my collaborators, Ijan and Paolo, both postdocs at Stanford, and Ehud and Matthew, who you know very well. Since previous speakers have already did a very nice introduction on this topic. Okay, it's not working. Sorry. Okay. I'll be a bit brief on the introduction. So yeah, we're in an era where experimentalists are approaching this ability to make continuous monitoring on a quantum system. In this example of Zlatko, as highlighted by Michael as well, he was able to observe. Sorry, I should take this off. He was able to observe the transition between a three-level system by counting the photons emitted. And he was really able to see the quantum jumps, the stochastic quantum jumps throughout time. And he was also able to effectively predict when a jump is about to happen and try to prevent that from happening. So this is quite impressive. Another example that is familiar to many of us is active quantum error correction, in which case, if you have a code block encoding some quantum information, you'll have to measure the system over and over again faster than the rate at which error accumulates in order to infer which errors have occurred and therefore preserve your quantum information. And of course, in this topic of measurement-induced phase transition, we now have two experiments that have realized that, and I'll get to them. So yeah, I think it's timely to think about such monitor systems in a more general sense. However, I'm still going to focus on this simple toy model, which we call a hybrid circuit. So this is a qubit model with qubits laid out on a one-dimensional chain. We have these unitary gates arranged in this brickwork pattern, and in between these, each layer of brickwork unitaries, we have measurements made at a probability p per qubit per time step. So an important thing in this model, in defining this model, is that we're focusing on quantum trajectory dynamics, meaning that whenever you make a measurement, you're going to take that measurement down and write it down on a notebook. And therefore, if, for example, if you make the jth measurement, the wave function will be collapsed after making this measurement. And the probability of that measurement outcome to occur will be according to the Born's rule, for example. And this is represented with this function, with this equation, where you're collapsing the state and normalizing it. And for the purpose of my talk, let me fix a few notations. Let me denote L, the number of qubits, or the spatial extent of the circuit, or the length. T is the circuit depth, or the temporal extent of the circuit, and N to be the length of my measurement record, which is equal to the number of measurements, which is proportional to P times L times T. And I'll be focusing on regimes where the time of the depth of the circuit is proportional to the length of the circuit. The basic phase diagram of this model is as follows. So in the limit, when you are not making any measurements, there are only random unitaries, and random unitaries tends to increase entanglement. So at long times, you always get this volume law entangled state in which the entanglement is actually maximal. In the limit, when you're making measurements at rate p equals 1, you're basically at each time step, you're projecting your state into a product state, and there's no entanglement in that. So this is certainly area law entangled. And these two phases, it turns out the volume law entanglement at p equals 0 is stable to a small finite rate of measurement, and there's a continuous phase transition from this volume law entangled phase to the area law entangled phase at PC, at some critical value, and this phase transition is second order. And here I'm focusing on the pure initial state. So if I start with a pure initial state and with the measurements, my pure state is going to stay pure. And the observable I use to detect the phase transition is this average entanglement entropy. So for example, I took some subregion A compute the S of A for the wave function on a particular trajectory labeled by M, then I average that S of A over measurement of all the measurements weighted by their Born probability. And the numerical results on the right is from Clifford circuit simulation. We see that when P is smaller than PC, the entanglement scales has this particular form, which is LA plus LA to the power beta, where beta is about 1/3. So this volume law phase, even though the leading behavior is no different, is similar to the P equals 0 point, there's an interesting subleading correction to it that is sort of special to this setup. And at the critical point, the entropy scales logarithmically with the system size, and this is suggestive of a conformal field theory in 1+1 in a two-dimensional circuit. And when P is greater than PC, the entanglement scales. The entanglement is a constant that doesn't scale with the system size. Another useful picture, as pointed out by Michael and David Hughes, and is actually realized in this iron trap experiment, is instead of taking a pure initial state, I can take a maximum mixed initial state, identity matrix, in which case the entanglement transition in the steady state entanglement entropy becomes a purification transition. So when you're not making enough measurements, this initial state that is pure and having a finite entropy density remains, that is mixed, having a finite entropy density remains mixed for times that is exponential in the system size, and this is the mixed phase. When you're making a lot of measurements, you're constantly extracting entropy out of the system, and within a constant number of steps, your mixed state is going to be fully purified, and this is the pure phase. And the behavior I just described, the dependence of the purity on time, is shown in this figure on the left. And if you look at a given aspect ratio of the circuit, meaning that you should fix T over L, then the entropy density versus P has this nice behavior across the transition. And this is like an autoparameter. You can think of this entropy density as an autoparameter for the volume of phase, for the mixed phase, in fact, in this case. The nice thing about this formulation is that it helps one to think about the mixed phase as a dynamical quantum memory, in which case you can draw this kind of diagram on the left, which has been used in the context of, I guess, black hole physics by Hayden and Preskill. So the setup is that instead of the maximum mixed initial state, you purify it by a number of EPR pairs, and you send half of your qubits into the system and half of these qubits as your reference system, and you make measurements in the circuit, and you ask at long times, how much information am I going to extract by making a local measurement on a single qubit, a subregion A? And the mixed phase can roughly be thought of as a phase in which this dynamics is a natural encoder, in the sense that a local measurement, if this is a good code, then local measurement cannot extract any information from the reference. Or in a more quantitative way, you can look at this so-called decoupling condition. There'll be a code distance for this dynamically generated code, and whenever your subsystem size A, which is 1, is smaller than the code distance, the mutual information between the qubit A you're measuring and the reference qubit R is going to be 0, in which case the density matrix on row AR factorizes. And in this case, local measurements on A have no effect on the entanglement entropy of A union A bar, or the entropy of S of R. And this says that the mixed phase will be stable if the code distance goes to infinity, as L goes to infinity, as the code distance will always be large as compared to 1, which is the number of qubits you're measuring at each time. And so yeah, as I said, the measurements on A do not contain any information of the initial state as long as P is smaller than PC. So the mixed to pure phase, the mixed to pure transition, the purification transition, can now be interpreted as a phase transition between a coding phase and a non-coding phase. So the coding phase will be characterized by a finite code rate, which is the entropy density, and a code distance, which is proportional to L to the 1/3. And this is actually the same exponent for the subleading entropy in the volume law phase. And another very nice way of understanding the transition is using a mapping to statistical mechanics models. So here I'm drawing a circuit on the left, and on the right I'm drawing, some sort of a spin model. And if I want to look at the entanglement entropy of a subregion A on the final state, in my spin model language, that corresponds to inserting, two boundary condition changing operators at the endpoints of A. And in this case, I'm using Ising model as a simple picture. There are only two types of colors, blue and yellow. And yeah, you can see I'm coloring qubits inside A with a different color than qubits outside of A. And in this picture, the phase transition can be roughly thought of as a finite temperature ordering transition of this magnet. And as you can see, if you're in the low temperature phase, the entropy of A corresponds to the free energy cost of introducing this boundary condition changing operators. And if the spins are ordered at low temperature, a domain wall, a sharp domain wall, must be inserted in order to account for this boundary condition change. And the free energy of the domain wall will have a finite surface energy and transverse fluctuations. And this surface energy sigma will be interpreted as a code rate. So yeah, I'm just talking about a few different ways of interpreting the phase transition, which I believe Ehud or Michael have mentioned. Any questions so far?
Could you say what's the picture of the code distance scaling in this Starbuck mapping?
Oh, the code distance scaling is not obvious, but it just happens to be L to the 1/3.
Okay. What does it map to in the Starbuck?
It doesn't immediately map to anything in this picture, but if you want, it's like you're considering, if you're considering the entropy of A bar, so A is small, but A bar is large, then there can be two types of domain wall configurations that accounts for this boundary condition change. You can either have a domain wall like that. So sorry, I'm also having, qubits on the bottom. So in this purification picture, I'm sorry, I think I have some pictures. Let me just skip to that and. Oh, okay, sure. So yeah, so this picture is what I was talking about. So if I have R, I want to put it on the bottom. And if I consider the entropy of B, which is my A bar, there are two types of configurations that accounts for this boundary condition change. And the code distance is where this transition happens. So when the free energy of the two configurations become comparable. Yeah, so when this is very long, and when A is small, the configuration on the right where this periodic domain wall pulls off the top is more favorable. And that's when measurements on A do not have any effect. But yeah, back to this. Yeah, so yeah, let me mention again the problem of post-selection. I've emphasized that you have to look at quantum trajectories as labeled by these measurement outcomes, and that poses an intrinsic difficulty in experimentally accessing the phase transition. And that is because we're always looking at nonlinear functions of each trajectory, but not linear functions of that. And in order to measure a nonlinear function, you'll have to post-select on the measurement outcomes until you get, at least two copies of the same trajectory row of n, and then you can imagine performing some sort of interferometric measurements on the two copies, and you'll be able to estimate something like a second Renyi entropy. But because the measurements typically happen randomly, and there's no way you can control the evolution of this. So the probability of you getting two copies of the same trajectory is exponentially suppressed by n, which is a number of measurements. But there are also other types of nonlinear functions, for example, other than the entropy. For example, this so-called Edwards-Anderson autoparameter, which looks like the Edwards-Anderson autoparameter for spin glasses, where you're evaluating the ZZ correlation function on each trajectory, but you want to square it before you average it. So this is also difficult to probe naively, experimentally probe naively. And just to give you an idea of how hard it is, how costly it is to post-select, I want to quote this recent paper from Austin Minish's group at Caltech, where they were, performing this brute force post-selection, and after they have a collision of the measurement record, they perform a full tomography on the output state. So basically, for each random circuit, they have to perform 1,000 times 2 to the number of m, where m is the number of measurements, shots of the circuit. So you get 1,000 samples for each measurement record. And this is already the most resource-intensive quantum simulation on IBM machines. Even this is only L equals 5. But nevertheless, this is a very impressive experiment. Now let me talk about some ideas of using bulk measurement outcomes to access the transition. As I said, if you're not recording the measurements, you're not going to be able to see the transition, and your mixed state density matrix is going to evolve into an infinite temperature one at long times. So one way of using the bulk measurement outcomes is post-selection, as I've already mentioned. Another idea, I guess, which was implicit in this paper by Yaodong, Michael Gullins, Roman, Andreas David, and other people, is that you can look at, possibly look at the Shannon entropy of all the measurement outcomes, classical measurement outcomes, defined this way. And if you look at the Shannon entropy density, that is the Shannon entropy divided by the area of the circuit, you're going to have a non-singular piece of the free energy, and in the subleading contribution, you'll have a universal number divided by the correlation length squared near the transition. And if you fine-tune to the transition, you can presumably look for a finite size effect, a finite size scaling of this quantity, in which case you might hope for extracting the effective central charge, which is a universal number related to the transition. But this seems to be pretty hard. This seems to be as hard as reconstructing the entire distribution over M. And the third idea, which was first mentioned in this very nice paper by Yimu, Sungwon, and Ehud, is that you can actually compare the measurement records from two slightly different initial states. So the two initial state that took is the product state on one side, and the product state slightly perturbed on one single qubit on the other side. And here's a picture of the histogram, presumably the histogram of the measurement outcomes. And you can see if theta is only a bit different, the two probability distributions will be a bit different. And if you look at the KL divergence between the two measurement distributions, and you take the derivative with respect to theta, this is known as the Fisher information, and the Fisher information acts like a boundary magnetization of this problem, in which case, and that does have a signal of the phase transition, but it's still not clear how you actually go about and measure this in experiments. As summarized by Sebastian in his paper, it is an irony that you have measurements that tells you something about the system, but you still won't be able to detect the phase transition. And I think the reason for that is that we've been focusing on random circuits, and for random circuits, and when you're making measurements in a random circuit, the basis of the measurement changes from one step to the next. And in order to make sense of the measurement outcomes, it'll be much easier if you know the basis in which you're performing these measurements. So there's an idea of correlating quantum measurements with classical information about the circuit. There are two examples of this, I think. First, in the random Clifford circuit, can be decoded and accessed with a local probe. If the gates of the Clifford circuit are provided, essentially, they were able to decode the circuit completely in the trapped ion experiment. Another idea is to look at simpler circuits where there are no random unitaries anywhere, but which will allow you to decode it more easily. And this was explored in these papers. Well, the observable we use to do this is this squared correlator of ZZ correlation functions, and this is a model with Z2 symmetry. And there are many other approaches to addressing the post-selection problem. And the last point, correlating quantum measurements with classical info, reminds us of something that is familiar to many of us. That is the cross-entropy benchmark for random circuit sampling. So in this case, you have a random circuit, you run it many times, and you compute this FXEB, which is defined in this way. And the bit strings xj are sampled from the random circuit according to probability p of, according to whatever the probability the circuit is. There possibly noise in the circuit. But for each xj, you want to compute this probability p of xj from a classical simulation of the noiseless circuit. You look at, and at the end of the day, you collect many samples of this, you compute this quantity, and you'll be able to see if FXEB is 1, then your quantum circuit is perfect. The measurement outcome probability exactly matches your classical simulation, and that's very good. But if your quantum circuit is decoherent, then your FXEB is 0 or very small. Then you would say, oh, my quantum circuit is now dominated by noise rather than the coherent evolution of the random unitary gates. So in a sense, this is one example of correlating, quantum measurement outcomes with classical information. And want to, do something like that for our problem of measurement-induced space transition. And the setup we come up with is comparing two initial states. So we want to test one initial state against another. We consider a bulk circuit that is fixed, but we want to take two different initial states, rho or sigma, and we want to send rho through a quantum processor. We want to simulate that on a quantum computer, but sigma remains on a classical computer, and I want to simulate that with my classical simulation. The question we're asking is, can we tell the difference between the two initial states from the distribution over the mid-circuit measurements? And the quantity we use is this linear cross entropy between the bulk measurement outcomes. So now PM rho and PM sigma are the probability of observing n with initial state rho and sigma respectively, and I want to normalize it with this sum over n PM sigma squared, so that this quantity is equal to 1 if the two distributions are identical. So the hope is that chi, this quantity, this cross entropy as defined here, will be close to 1 when p is small in the volume law phase, in which case, as I said, it's a good code in the measurement. Do not reveal any information about the initial state, whereas chi, I would expect chi to be small in the error law phase, where you're making so many measurements, you can effectively learn, you can effectively distinguish the two initial states. And there's a clear procedure of sampling this ratio in practice, in experiments. I want to first run the classical simulation many times with the initial state sigma to estimate the denominator, and then I can run essentially the same cross-entropy benchmark for the random circuit sampling with the rho initial state on the quantum computer. But for each run, I compute Pm of sigma of the corresponding probability in my classical simulation, and this will give me an estimate of the numerator, and then I'll output the ratio. So in this protocol, there's no need of post-selection because I'm using all the measurement outcomes I can get. There's no decoding, presumably, and there's no feedback that I need to do or tomography. So in principle, in order to estimate this quantity to some constant precision, polynomial many samples can be enough. But in practice we run some numerics, and it doesn't look very good on the random hard circuit due to the large numerical fluctuations, and also the classical simulation takes a time that is exponentially long in the system size, so this is also prohibitive. So, but we can simplify it a little bit without losing all the interesting things. So there are a few further considerations. We want to take the random unitary gates in the bulk to be Clifford gates, and we want to let sigma to be a fixed stabilizer state, whereas rho is unspecified or unknown. And in this case, I can rewrite the cross entropy in this way, and I want to compute this quantity in the box, which I call Qm of sigma. And because sigma is a stabilizer state, this quantity is going to be very easy to compute. And also, this quantity Q is either 0 or 1 for a stabilizer circuit, so you can do really good statistics without many samples of running rho on the quantum computer. And I want to say this is also nice in that although we still need some classical computation, this classical computation is a very weak one. So the only thing you have to agree between the classical computation and the quantum simulation is the bulk, whereas the initial state rho is essentially unknown to my classical computer. And yeah, so in general, rho is not a stabilizer state, so it's going to be very, very difficult to simulate. But nevertheless, I'm still going to compare that with my easy simulation sigma and get some information about the measurement, about the transition. And there's also a third point, which is U encoding, which is nice, but maybe not necessary. So we want to have a pre-encoding stage before I start to run the hybrid circuit, so that the idea is that if you have a small difference between rho and sigma, they'll become large typically after you run this encoding step. And we'll see how this works in a minute. And here's some numerical, sorry, yeah, sure. Here's some numerical result. I'm choosing rho and sigma to be both stabilizer states just to get scalable numerics, and it seems that it matches our expectation that it is very close to 1 in the volume law phase, and it goes to a smaller, it goes to a constant, order 1 constant is smaller than 1 when p is greater than pc. And near the critical point, it has this characteristic scaling form of second order phase transition, which is pretty nice. And also we look at the noise, the variance of this quantity against the number of samples, and it scales nicely against like as 1 over square root of m. So that is also good. And to understand why this should behave like that and why this is a good detection of the phase transition, let me use the mapping to statistical mechanics model. It's developed by in previous work. The first step is to replace the annealed average. Replace the quenched average, which we do not know how to do, by an annealed average, which we do know how to do. And this is the result. And as you probably know, many of you know, after this average, I get an Ising model. The temperature T will be played by the measurement rate P, and there will be the ordering transition between the ferromagnetic and the paramagnetic phases will be the 2 phases in the circuit. And the ratio, the chi, is now a ratio between 2 partition functions. The numerator has all the spins on the top boundary being up and all the spins on the lower boundary being up, and the denominator has these 2 summations. And the additional term is when you have all the spins on the top being up and all the spins on the bottom being down. And if you're in the volume law phase or the mixed phase, again, a domain wall must be introduced in order to account for this boundary condition change. And that domain wall has a free energy that is extensive now. Whereas in the area law phase, the domain wall has a constant free energy. And that gives you this behavior of chi in the 2 phases and near the transition. And we can also discuss the effect of noise. And the noise acts like a depolarizing field. The depolarizing noise acts like a magnetic field that breaks the Z2 symmetry in the Ising model, which suppresses the chi everywhere in the phase diagram. But nevertheless, you can still see some, numerically we checked the depolarizing noise, which is very simple, but we're able to still see some signal of the transition when the system size is not too large. When the system size is not too large and when the error rate, the depolarizing noise rate is not too large. And there are further simplifications, which is saying we can get rid of the pre-scrambling, pre-encoding unitary, and we can have a shallower circuit without losing the phase transition. Here's a summary. We have a new protocol which could potentially allow scalable experimental demonstration of the measurement-induced phase transition. It uses an interpretation of the phase transition in the distinguishability of the measurement records in the bulk, rather than the scaling of entanglement in a steady state. And we only use classical measurement results, and that does not require any post-selection decoding, feedback, or tomography. And it can tolerate weak noise. And there's other simplifications to make it easier to implement on an experimental platform. And yeah, I guess the question is, can we really see it on currently available devices? And of course, in that case, we have to worry about real errors, and we might want to perform readout error mitigation and stuff like that. So this is really unknown. There are some interesting open questions, which I'll leave at this slide, and I'm happy to take questions.
Hi, thank you for the very nice talk. So, so the linear cross entropy that you define here is slightly different from the one that Google used, for example, by the denominator. And because of that, it seems like in the Google case, if you have the ideal circuit, you get 1, and you have a completely noisy one, you get 0.
Right.
But in your case, you get 1 in both limits.
I get 1 in one phase and a constant smaller than 1.
No, I'm saying if you plug in P of sigma equals to 1 over 2 to the n, this is identically 1.
Yeah, if sigma is equal to rho, it's identically 1, right?
No, also if sigma is equal to that entity, you get, or rather, if you have a completely decoherent state, you'll get xib equals to 1. So it seems like this should go to 1 in the limit of total noise, and then the data you showed with noise had curves kind of going down. So I guess.
Yeah, so I'm only including noise in my simulation of the rho circuit, but not in the sigma circuit. So my sigma circuit is still noiseless.
Okay.
Yeah, if you include noise in both, yeah, you'll go to 1.
Okay.
That's right.
Thanks.
I think there's a question on Zoom. David, maybe.
Yeah, do you hear me?
Yeah.
Is this, are you seeing the phase transition in a typical trajectory? You were mentioning an Ising, mapping to an Ising model, and I was wondering if you were seeing what amounts to the Ising transition, which would be sort of a 2 replica type transition, not the typical trajectory, or am I misunderstanding?
Right, the Ising is just a picture. The numerics still done for the typical transition, typical trajectories, if that's.
Okay, thank you.
Sure.
Other questions? Have you thought of any noise mitigation strategies?
Yeah, so I guess what I know about readout error mitigation was really from this paper from Caltech. I don't know all the details, but it seems that they were able to perform the readout error mitigation pretty effectively. So I was hoping that, yeah, this protocol I proposed seems to be simpler than this one. So whatever they were able to do should be applicable to this protocol, right?
So another question on Zoom.
Hey, thanks for your talk. One question I have here is to do with how well this cross entropy averages. So maybe you're saved some kind of Clifford circuits here, but naively, I think that the p sigmas would have an extremely broad distribution.
Yeah, not in the case of Clifford circuits. In the Clifford circuits, this ratio, I highlighted in boxes, either 0 or 1, so it's really easy to average. In general, we don't really know. Numerics doesn't look very well, and
right. Okay, so that would explain what's going on in Haas circuits, where you'd think it would have like a log normal distribution.
Yeah.
Right. Okay. Thanks.
Yeah. So can you just? I guess this works in this non-adversarial setting, but it seems like you could probably spoof. Can you talk about spoofing this cross entropy score? It seems like the quantum simulator could just be feeding you something easy to simulate, or
yeah, it may be easy to simulate.
So can you comment on verification, or is
verifying whether it is difficult to
right? Because this is not right. Yeah, it's not verify. It's not getting a high score on this doesn't verify that the quantum simulator did the correct.
Yeah, so we didn't worry too much about whether this is hard to simulate classically. Our purpose was just to see the transition. But yeah, what we did look at is the output state. So for example, if you have an output state in a volume phase, and you measure every qubit, measure out every qubit, and you look at the proper distribution of all the bit strings, that does look a bit non-trivial, but we have no idea how to sample from that distribution without post-selection.
Thanks. Yeah, that's interesting.
To get a reliable statistics for the plot you generated for cross entropy, how does the number of measurements and like classical computation scale with the system size?
Sorry, say that again. I couldn't really.
Oh, to get the reliable statistics for the plot you generated
Okay.
for the cross entropy, how does the number of measurements and number of like quantum circuit iteration and the
Okay. Yeah.
and the classical computation scales with the system size?
So yeah. So the number of circuits, I think I always took 300 for each data point, and the number of samples is always 100. I guess it's not too small, but it's also not terrible. And the simulation, the classical simulation of the Clifford circuit is some polynomial of the system size, so L squared or L cubed.
And how important is the choice of sigma?
It's not very important as long as it's different from rho. It should generically work.
I guess it only changes that like a constant value in the area.
Yeah, it might change the constant value. You're right, okay. But this is not very universal.
I see.
Right.
Thank you.
Okay, if there are no other questions, let's thank Yaodong and all the speakers today.